Hello everyone, welcome back to our course on vibration and noise control ME22088. Today we are embarking on Unit 3. Specifically, we, are, we will be diving into a useful approximate method for determining natural frequency of a system with multiple masses, that is Dunkerley's method. It is part of Unit 3. It is lecture number 8 in Unit 3 series. In this unit, we will explore the fundamental principle behind Dunkerley's method and learn how to apply it to practical vibration analysis problems. You can see on the slide a visual representation of a beam with multiple masses, which is a typical scenario where the Dunkerley's method proves to be quite effective in estimating fundamental natural frequency. I am Dr. C. Sendamarakannan, Associate Professor in the Department of Mechanical Engineering at SVC. I will be guiding you through this topic. So let's get started and understand the core concepts of the Dunkerley's method. Let's proceed to the next slide. Now, let's delve into the fundamental concept behind the Dunkerley's method. This method provides us with a powerful tool to estimate the fundamental natural frequency of complex systems, particularly those with multiple degrees of freedoms or composite structures. The key principle that Dunkerley method relies upon is the observation that for many complex vibratory systems, the higher natural frequencies are significantly larger compared to the fundamental or the first natural frequency. This allows us to make certain approximations to simplify the analysis. On this slide, you see the general frequency equation for an n degree of freedom system. The equation is represented by the determinant of minus stiffness matrix plus omega square mass matrix being equal to 0 or equivalently same determinant of minus inverse of omega square into identity matrix plus A matrix, that is flexibility matrix, into mass matrix, that is also equal to 0, forms the basis of our vibration analysis. Let's see the terms here, that is K represents stiffness matrix of the system to deformation, which is exactly describing resistance offered by the system towards the deformation. M is the mass matrix indicating mass distribution within the system, where omega is the natural frequency we are trying to find and I is the identity matrix. The equation is also expressed in terms of lambda, that is equal to 1 by omega square. This form is often more convenient when applying the Dunkerley's method. Here, determinant A is flexibility matrix, which is the inverse of the stiffness matrix. The flexibility matrix essentially tells us how much the system will deform under a unit load. Dunkerley's method cleverly utilizes this general frequency equation and the aforementioned principle about relative magnitudes of natural frequencies to arrive at a simplified way to estimate the fundamental frequency. In the subsequent slides, we will see how this simplification is achieved and how we can apply this method to solve practical problems. So please let me see from the next slide onwards the derivation and application of the Dunkerley's method. Building upon the frequency equation we discussed in the last slide, let's now consider a lumped mass system. For such a systems, the mass matrix M becomes diagonal elements represents the individual masses at each degree of freedom and all of diagonal elements are 0. Substituting this diagonal mass matrix into our frequency equation, that is in the previous slide we have minus 1 by omega square into identity matrix. So this is minus 1 by omega square identity matrix plus A flexibility matrix and mass matrix equal to 0. We get this form, that is it is shown here, and also if we multiplying this identity matrix by 1 by omega square and added this together to the flexibility matrix and the diagonal mass matrix after the mass and flexibility matrix multiplication, we will expand this determinant. We arrive at the equation that is given below. Notice the structure of the resulting determinant, that is the diagonal elements are of the form minus 1 by omega square plus A II mi. What is that? A represents the flexibility coefficient at the ith mass and mi is the ith mass, that is mass. Flexibility coefficient at ith mass and mass at also the ith mass. The off diagonal elements involves the product of the flexibility coefficient between different masses and the corresponding mass. For instance, the element in the first row and second column is A1 to M2. What is the meaning of this? That is flexibility matrix at 1, mass at 2. Expanding this determinant will be yield a polynomial equation in terms of 1 by omega square. The root of this polynomial equation will give us the values of omega square corresponding to the system's natural frequencies. However, solving this higher order polynomial can be complex, especially for systems with a large number of degrees of freedom. This is where the power of the Dunkerley method comes in, as it provides a way to approximate the fundamental frequency without needing to solve this entire polynomial equation. Let me see that in the next slide. As we discussed, expanding the determinant from the previous slide leads us to this polynomial equation. Here it is the general form. You can observe that in the nth degree of the polynomial in terms of 1 by omega square, where n represents number of degrees of freedom of our system. The roots of this polynomial equations are given as 1 by omega n square and 1 by omega 2 square and so on up to 1 by omega nth term square. These roots correspond to the reciprocals of the squares of the system's natural frequencies. So omega 1 is the first natural frequency, omega 2 is the second natural frequency, and so on. A crucial property of this polynomial equation is the relationship between their coefficients and the roots. For a polynomial of the form which is given here, the coefficient of the 1 by omega square to the power of n minus 1, this term, will be equal to the negative of the sum of the roots. So, looking at our expanded equations, we can see that the coefficient of 1 by omega square to the power of n minus 1, the term will be equal to a11 m1 plus a22 m2. Therefore, we can write sum of the roots in this form. This equation is the cornerstone of the Dunkerley's method. Recall that we mentioned earlier that for many systems, higher natural frequencies are significantly larger than the fundamental frequency. This implies omega 2, omega 3 and so on are much greater value than omega n. So Dunkerley's method leverages this fact by approximating the sum of these natural frequencies. This is because the contribution from the higher frequencies are considered negligible. In this slide, we are coming to conclude the Dunkerley's formula. Let's see. As discussed in the previous slide, by equating the coefficients of 1 by omega square terms, we arrived at the relationship, that is 1 by omega square equal to A11 M1 plus A22 M2 plus so on till this A Mn. Due to the fact that is generally much larger frequencies, fundamental frequency is going to be very less compared to the other frequencies. So larger frequency contributions are very less, that is very small. Thus we can approximate the sum of the terms, the first terms alone, leading to the Dunkerley's formula 1 by omega square equal to A1 M1 plus A2 M2 and so on. This equation is the essence of the Dunkerley's method. This allows us to estimate fundamental natural frequency by summing up the products of the direct flexible coefficient and the corresponding mass for each mass in the system. Once we calculate the sum on the right hand side, we can easily find the approximate value of omega 1. It is important to note that the fundamental frequency obtained using Dunkerley's formula will always be slightly smaller than the exact value. This is because we have neglected the positive contributions from the higher natural frequency. Finally, let's consider that this term II, that is flexibility coefficient of ith flexibility coefficient at ith mass, that is the direct flexibility coefficient at the location of mass I. Inverse of this represents stiffness at that location. Therefore, this term is equivalent to K divided by M. This term is equal to K divided by Mi, that is K subscript of I divided by M suffix of I, which is the square of the natural frequency of a single degree of freedom system consisting of mass M and stiffness K. So this provides an intuitive way to understand Dunkerley's method as combining the effects of individual masses on the overall fundamental frequency. Now we understood the theoretical basis of the Dunkerley's method. Let's apply it to a practical example. Consider the system shown in this figure. It consists of 3 masses connected by springs. Our goal is to find the lowest natural frequency of the system using Dunkerley's formula. To apply Dunkerley's formula, we need to consider each mass individually as a single degree of freedom systems. That is, the figure shows the individual components. For the first mass of 4m, it is supported by 2 springs in series, each with stiffness 3K. That is, the equivalent spring stiffness will be equivalent to 1 by 3K plus 1 by K. So what we will get? We will get the equation in terms of K by M. So the natural frequency of this individual system will become as, since it is going to be equivalent frequency, that is 3K by 2. So omega equal to root of 3K by 4M. The slide directly uses this value, which would be the case if there was only one spring stiffness 3K supporting the mass 4m. So it is very important. We are only considering the 4m mass is connected to 3k. We are neglecting the k term at this point. Similarly, for the second mass also, it is supported by spring of stiffness k only. We are not considered any other terms 3k or another k. Therefore, natural frequency second mass is going to be k divided by 2m. For the third mass, it is supported by spring with stiffness k. Hence, its natural frequency omega 3 equal to root of k by m. We apply the Dunkerley's formula, which states 1 by omega square equal to 1 by omega 1 square, that is the first mass frequency, plus 1 by omega 2 square second mass frequency, plus 1 by omega 3 square third mass frequency root of k by m. By substituting all these values omega 1, omega 2, omega 3 in this equation, it has been found that 1 by omega square equal to 3m by 3k. Sorry, it is 13m by 3k. Okay, so this value further if we resolved, we will get omega equal to 0.475 root of k by m. That is, the approximate lowest natural frequency is omega equal to 0.475 times of root of k by m. If you know the k and m, we can substitute and we will get what is going to be stiffness. There will be slight differences while rounding off or minor variation in the initial interpretation of the system components like this. However, the process of applying Dunkerley's formula remains the same. So we calculate the natural frequencies of the individual mass spring systems, then sum the reciprocals of the squares to find the reciprocal of the square of the approximate lowest natural frequency of the combined systems. This example shows how the Dunkerley's method provides a relatively very simplest way to estimate fundamental frequency of a multi-degree of freedom system. Dunkerley's method is not limited to simple spring mass systems. It can also be effectively used to estimate the natural frequency of transverse vibration for shafts carrying multiple point loads and even uniformly distributed loads such as the shaft own mass itself. Here in this slide, we are going to discuss how to use Dunkerley's formula for the determination of natural frequency of shaft. According to Dunkerley's formula, the reciprocal of the square of the natural frequency of the transverse vibration of the shaft is denoted as and approximately equal to the sum of the reciprocals of the squares of the natural frequency of individual components or loads. Hence, you can see that where f suffix n represents natural frequency of transverse vibration of entire shaft, considering all the point loads and the uniformly distributed load. This frequency we want to estimate, and it is very important to know that Fn1, Fn2, Fn3 till Fn is nothing but natural frequencies of transverse vibration if only each individual point load were present on the system or shaft. We would calculate these frequencies by considering each point load separately. At last, where f suffix ns represents natural frequency of transverse vibration due to uniformly distributed load, which could be mass of the shaft itself. Therefore, the standard formulas available to calculate the frequency is depending on the shaft boundary condition, for example, simply supported or fixed end. The formula essentially states that the overall flexibility of the system or shaft is represented by the inverse of the square of the natural frequency, which is equivalent to sum of the flexibilities contributed by each individual point load and the distributed load. This extension of Dunkerley's method highlights its versatility in handling more complex scenarios encountered in real-world engineering applications such as rotating machineries. By calculating individual natural frequencies for each load and the shaft's own mass, we can get a good approximation of the fundamental transverse vibration frequency of the entire system. In this subsequent lecture, we can delve into an example how to calculate individual natural frequency for point load and also UDL, that is uniformly distributed load system configurations. Let's consider a more specific example of a shaft loaded with multiple points denoted as W1, W2 and so on till omega 3, subjected to uniform distributed load, that is small w per unit length. To apply Dunkerley's method in this context, we need to determine natural frequency contribution from each of these loads individually. A key concept here is the static deflection caused by each load when acting alone on the shaft. Let's denote the static deflection due to the load W1 as del 1, W2 as del 2, W3 as del 3, and the static deflection due to the uniformly distributed load will be calculated in terms of del suffix s. There is a well-established relationship between natural frequency of transverse vibration caused by a single point load and its static deflection, that is natural frequency due to because of single point load equal to 0.4985 divided by root of static deflection due to because of point load alone. In the similar way, the natural frequency of transverse vibration due to uniformly distributed load or weight of the shaft is given as 0.5615 divided by root of del s, that is static deflection due to because of the weight of the shaft. These formulas will be very much useful to find the natural frequency of the entire shaft system. Let's take the expressions for the natural frequencies of a point load and a uniform distributed load in terms of their static deflections, which we saw in the previous slide. So as per that, the formula for the shaft with multiplied load is given as represented like this, and then we are substituting what is going to be the natural frequency, that is we seen in the previous slide, that is equal to root of del divided by 0.4985. So substitute for each point load in this equation, and also the natural frequency for the static load, otherwise static deflection or weight of the shaft, that is also substituted. Simplifying this term, in sense we are commonly taking 1 by 0.4985, then it will equivalent to del 1 plus del 2 plus del 3 plus del s divided by 1.27. If you multiply this with this 0.4985 square into 1.27, we will get the value equivalent to 0.5615 to the square. Further simplifying this and this, we will get the final Dunkerley equation, which will be almost used to most of the shaft system, which is simply subplotted. That is, this is the final formula for any shaft system to be used having the multiple point load and the static load due to because of the weight of the shaft. If the weight of the shaft is not given, this term can be neglected. So such a way that This is our final formula. Natural frequency of the shaft due to because of the multiple load considering its own weight is equivalent to 0.4985 divided by root of del 1 plus del 2 plus del 3 so on till del n, and also using the weight of the shaft del s divided by 1.27. The next slide we will solve a small problem. Here, before solving a problem, let me have some conclusion. First conclusion is, as per the Dunkerley's method, if there is no uniformly distributed load, that is, if the mass of the shaft is negligible, then del S equal to 0. I already told you that this will be removed. So the Dunkerley's formula is simplified. This means we need to consider only static deflection caused by the individual point loads to estimate the fundamental natural frequency. The second note is to provide a useful formula for calculating static deflection of a simply supported shaft subjected to a point load W. That is, static deflection of a simply supported shaft subjected to a point load W. So this static deflection formula will be vary depending upon the shaft supporting condition. This is simply supported condition formula, that is del equal to W A square B square divided by 3 in terms of Young's modulus, moment of inertia and total length of the shaft, where A and B is nothing but it will be represented like this, that is the point load is going to be somewhere away in the center. Then the distance from the left hand side will be equivalent to A. Then the remaining distance will be equivalent to B. The total length of the shaft is equivalent to L. So this formula is very much crucial, which is allowing us to calculate individual static deflection for the simply supported shaft, provided we know the magnitude of the load and its location along the shaft, as well as the material and geometric properties of the shaft. Once we have the static deflection, we can ready to do and apply the Dunkerley's formula. These notes 1 and 2 are more practical guidance are using Dunkerley's method for shaft vibration analysis, especially for the common case of a simply supported shaft. Let's consider a numerical example to solidify our understanding how to apply Dunkerley's method to shaft with point loads. As per this problem, we have a shaft with a diameter 50 mm and a length of 3 meters. This shaft is simply supported at the ends and carries 3 loads, that is 1000 Newton at 1 meter, 1500 Newton at 2 meters, 750 Newton at 2.5 meters from the left supports. The Young's modulus for the shaft material is given as 200 giganewton per meter square. Our task is to find the frequency of transverse vibration of this particular shaft. As per the given data, we can write small d equal to 50 mm, that is represented as 0.05 meter. Length of the shaft is 3 meter. The load W1 is 1000 Newton, load W2 is 1500 Newton, load W3 is 750 Newton, where Young's modulus we can rewrite as 200 into 10 power 9 Newton per meter square. The first step is to calculate moment of inertia of the shaft circular cross section, which is commonly used for all loads. So we are calculating moment of inertia I equal to pi by 64 d power 4. the diameter of the shaft is given as 0.05 meter. So while substitute the diameter of the shaft and solving this, we are getting moment of inertia of the shaft is 0.307 into 10 power minus 6 meter power 4. This is the value of the moment of inertia which is to be substituted for each and every static deflection due to because of the loads. Let's calculate the static deflection due to because of the first load, where W1 is 1000 Newton, which is located at A1, that is 1 meter from the left support. Since the total length of the shaft is 3 meter, if A equal to 1 meter, then B equal to 2 meter. Okay, so we have to substitute that in this formula. So W equal to 1000 we have to substitute, A equal to 1 meter we have to substitute, B equal to 2 meter we have to substitute. Young's modulus, moment of inertia, ALR commonly for all the loads. So as calculating, we are getting the static deflection value delta 1 as 7.24 into 10 power minus 3 meter. There was this is a approximation value. In the next slide, we will calculate static deflection due to 1500 Newton. In this slide, we are calculating static deflection due to second load, that is W2 1500 Newton, located at a distance of 2 meter equal to A equal to 2 meter, B equal to 1 meter. Again using the same static deflection formula, substituting all these values 1500 to 1 and the denominator remains same. The value of del 2 is equal to 10.86 10 power minus 3 meter. So in the next slide we will calculate static deflection due to the third load. Finally, we calculate the static deflection due to the third load, that is 750 Newton, located at a distance of 2.5 meter, that is equivalent to A, B equal to 0.5 meter. Using the same static deflection formula, substituting the value W equal to 750, A equal to 2.5 meter, B equal to 0.5 meter, and all other denominator value remains same. We are calculating and find that static deflection due to 750 Newton is 2.12 10 power minus 3 meter. Now we substitute all this deflection del 1, del 2, del 3 in the Dunkerley's formula. Finally, we can calculate the frequency of transverse vibration using Dunkerley's formula for the shaft with point loads. Okay, we are substituting the values del 1 7.24 into 10 power minus 3, del 2 10.86 into 10 power minus 3, del 3 2.12 into 10 power minus 3. By substituting this and taking the summation of all this value and taking square root, we are getting the denominator value 0.1422. Numerator is divided by the denominator. We are getting the natural frequency is 3.5 Hz. So approximate frequency of the transverse vibration of this shaft, the given shaft, using Dunkerley's method is 3.5 Hz. This example demonstrates a practical application of the Dunkerley's method for determining natural frequency of the shaft carrying multiple loads. To summarize this lecture on the Dunkerley's method, we have learned that it is a powerful approximate technique used to estimate the fundamental natural frequency of a system with multiple masses or a continuous system like a shaft with several loads. The method is based on the principle that for many systems, higher natural frequencies are significantly larger than the fundamental frequency. We saw how the Dunkerley's formula is derived from the general frequency equation, by considering the relationship between the roots and coefficients of the polynomial equation obtained after expanding the determinant. We also explored how the method can be applied to both discrete lumped mass systems and continuous systems like shaft, carrying point loads and uniformly distributed loads by considering individual natural frequencies or static deflection caused by each component or load. Finally, we worked a numerical example for better understanding the Dunkerley's principle. So, Dunkerley's method provides a relatively simple and effective way to get a good approximation of the fundamental natural frequency, which is often the most important frequency in any vibration analysis. Thank you for your attention. I hope you find this lecture on the Dunkerley's method informative and useful. If you have any question, please feel free to ask me.